Now let us connect fields and vector spaces together. First of all, the definition says a vector space includes a field of scalars, an abelian group, a mapping that maps f v to v by using a scalar multiplication here, which satisfies the following. You have distributive properties, C distributed over the summation of two vectors, C1 plus C2, these two are scalars, times V can be written as C1V plus C2V, C1 times C2V can be written as C1 times C2V, and 1 times V is equal to V. In this case, we say that, hey, V is a vector space on field F. Have you seen this before? Many times. So remember, F is a field. We talked about fields before. Suppose you have, for example, Q, rationals, or R. Those are examples of fields that we discussed in this class. Right. The collection of n-tuples. We represent this guy by f to the n, which is basically the Cartesian product between f and f. Continue this process n times, and this guy is equal to the collection of x1, x2, x3, x sub n, such that xi each belongs to field f. I is bounded between 1 and n. We can define the operation vector addition and scalar multiplication as below. So the vector addition is defined as suppose you have u, which is basically x1, so u is x1, x2, x3, and xn, and v is defined as, for example, y1, let's change these grades, it doesn't matter, y1, y2, y3, and yn. We can add u and v together, you get x1 plus y1, x2 plus y2, and x3 plus y3, and so on, xn plus yn. So this is your vector addition. And the scalar multiplication is defined as Cu. For example, it is Cx1, Cx2, and Cxn. So as you can see, we defined a vector space V equals to the collection of all n-tuples f to the n, and it is basically a vector space, and f is a vector. In a special case, if you consider f to be R, then you have a vector space, which is n-tuples with real values.